approximately equal to f times x because we haven't done it. And we'll call this the finite difference. I don't know how I'm going to say that. I'm going to say f b of x. Okay? This is called a finite difference. Because it's over a finite interval of space. Delta x is not 0. And we're not taking the limit as delta x equals 0. We're simply saying, all right, delta x is sufficiently small that we can define a derivative. So, this is an equation now. Let's drop this. So this thing is an equation, or we can basically put this in for any xi. We'll just say approximately equal there. So let's have a function like this. All right? And let's calculate, this is xi, and this is xi plus epsilon. All right, and this is f of xi, and this is f of xi plus epsilon. So the finite difference is simply going to be the slope between those 2 points. Right? It's not the tangent, it's the secant. So, now we have a series of equations at every point here. And notice that we are registering the finite difference at the point xi. We're using a point ahead of it to estimate the point at xi. So this is what's called a forward difference. Okay? We could do the same thing with a backward difference, right? We could basically say f of xi minus f of xi minus epsilon, and that would be a backward difference. Or we could do a central difference, where we said central difference, what would be the equation of the central difference? Anybody? So we're basically, we have a point here, xi minus epsilon. What's the equation of a central difference? Right. Exactly. So the central difference is f of xi plus epsilon minus f of xi minus epsilon divided by 2 epsilon. It's wider, and it's a bigger, it's over a larger distance, but it's centered at the point. So then we have this slope, which is more accurate. In this case, it's actually the central difference that's wrong. But I can give you cases where the forward difference is better. I can give you cases where the backwards difference is better. All right? It's really a choice of what you want to do, what you want to look at. Okay, so that's basically the way that we calculate a derivative. Okay? So how do we represent that as a matrix problem? Well, we've got these series of equations. Let's just do a forward difference to make it simpler. And we'll multiply Okay? So how do we represent that as a matrix equation? Well, we're applying this to f of xi, right? So what is right here? This will be f of x1, f of x1 plus epsilon, f of x1 plus n epsilon. Okay, we're going to do n points spaced equally, n points epsilon apart. So this is going to represent f prime of x at these points xi. So what's the matrix on the other side? What does it look like? What's in here? Well, the very first point is f prime of x1. Remember, we're calculating a forward difference here. So if I put 1 for f of x1 and minus 1 for f of x1 plus, I'm sorry, 1 minus 1, sorry. Those are the first two elements of the matrix that I'm multiplying f of x1 and f of x1 plus epsilon. Right? So I'm going to get, if I do that and then have the rest of these zeros, then I'm going to get this first equation right here. It's going to be minus 1 times f of x1 plus 1 times f of x1 plus epsilon. So I'm going to get f of x1 plus epsilon minus f of x1. Well, that's not quite the finite difference. I've got to multiply by 1 over epsilon, divide by epsilon. So I can basically get rid of this and put an epsilon, 1 over epsilon, sorry. Pre-multiply or post-multiply, multiply by a constant, this matrix like that. What about the next point? Pretty simple. Right? And we have two zeros. Minus 1, so forth, down to all zeros. And the tricky part here is that we actually have to use minus 1, and we don't have another endpoint, right? The next endpoint is going to be 0. So that's an example of a matrix formulation of a forward difference. Matrix multiply, all right? So now you can do all kinds of cool things with that, right? In MATLAB. This is just of the form x equals y, where x is f of x, and this is f prime of x, approximately. And this is often called a finite difference stencil. Because it's essentially the same operation acting on the function over and over and over again, you can do this very efficiently in the computer. You can actually use the graphics processing unit on your computer to calculate this. Okay, so ax equals y, again, is the equation. If I want to invert a, x is approximately ay, that'll be the antiderivative or the integral. If I want to apply a twice, I get the first derivative, second derivative, or I want to apply 3 times, I can get the third derivative, whatever I want to do. Each time I do one of these finite differences, I'm going to have less points there. Not less points, I'm going to have inaccuracies at the end. Now, what if I wanted to do a central difference? How would that look? Well, there is no central difference really for the first point, right? It's kind of meaningless. What about the second point? So I'm just going to have stencil that looks like this. And I have a 0 in between. I'm only going to use the values bracketed at the point that I'm calculating the derivative. And so you can imagine that I can do play all kinds of games with this stencil. I don't have to make it -1 and 1. Maybe there's a function where it's actually better to change the coefficients. Maybe I want to use more than 2 points to calculate the difference. Maybe I want to use 8 points. This whole operation is a science